Hi guys, today we're going to go ahead and go through the next section of Unit 1. We're going to talk about atomic structure and electron configuration. So a lot of this will be review from previous years. So let's go ahead and get started. Let's go ahead and take a look at the top of our notes really quickly. Protons, neutrons, electrons. You need to know where they are. You need to know their charges and what that does for the charge of different parts of the atom. So our protons are going to be positively charged. Neutrons have no charge. Because the protons are in the nucleus is positively charged. We also have our electrons. That's what we're going to focus on a lot today, of where they're located and how they're structured within the atom. But we know, of course, that they are negatively charged and they're located in energy levels. And so today we are going to talk about those energy levels and what's inside of those energy levels, the sublevels and orbitals and all kinds of different things that are going on. There's a lot to the story about electrons and where they're located. A really important thing in AP Chemistry. They love to ask you questions on the AP exam and say, using Coulomb's law, explain, why certain things happen. And we're going to come across a lot of these questions as we go through this unit and future units. Concepts. It is all conceptual things that you need to know about Coulomb's law. Okay, so first thing that you need to understand to help us understand this law is something that you already know, and that is that opposite charges attract, like charges repel. So that means when we're talking about protons and electrons, they're oppositely charged. So within an atom, they do have a certain force of attraction towards one another. And the amount of attraction that they have is directly proportional to a couple different things. So the charge of whether it's protons in the nucleus, or if we're talking about ions that have certain charges. So the greater the charge, the greater that attraction is going to be. So like if I have something that has a charge of, +1 and something that has a charge of -1, they're going to have a certain amount of attraction. But if I have something that has a charge of plus, is going to be stronger because those charges are bigger. So it has to do with the charges. The greater the charge, the greater the force of attraction. So actually we'll go ahead and fill this in right here. This should say stronger force of attraction, or repulsion if we're talking about charges that are the same. Also, it is inversely proportional to the distance between the charges. That means the closer they get together, the stronger that force of attraction is going to be. And the farther apart they get, the weaker it's going to be. Now, this equation, Q represents the charge, and R represents the distance between the two charges. As far as this equation goes, they don't give it to you on the equation sheet. And it's not one that you need to memorize. It's not one that you actually ever have to do any calculations with. It's just one that you have to understand conceptually. And that concept is just the greater the charge, the stronger the force of attraction. And then the closer they are together, the stronger the force of attraction will be as well. So just understand those concepts. Let's go ahead and talk about those electrons. So we're going to talk about what's called the quantum mechanical model for electrons, which is just really the location of the electrons. Where are they? So we've already talked about the fact that electrons are in energy levels. Now, something that we talked about in your previous chemistry classes is that within energy levels, there are these sublevels. And then even within sublevels, there are orbitals that hold electrons. And so we need to understand all of those details, like what are the energy levels, what are the sublevels, how many orbitals does each sublevel have, and so on. So let's just go ahead and go down here. Basically all this stuff at the top I just kind of summarized. So this letter N, when we see this and we're talking about electron energy levels, is just what main energy level are we talking about? Is it energy level 1, energy level 2, 3, or 4? And it can go all the way up to 7 energy levels. Each energy level has a different number of sublevels. And our sublevels have letters to represent those different sublevels, and they have different shapes. So those sublevels are S, P, D, and F, and the energy levels have different numbers of sublevels. So energy level number 1 has an S sublevel. Energy level number 2 has an S and a P sublevel. Energy level 3, S, P, and D. And energy level 4, really all the way through 7, are all going to have S, P, D, and F sublevels. And within each sublevel, there is a certain number of orbitals. You can think of orbitals like rooms that hold electrons. And so because of the shape of each of these different sublevels, they can hold different numbers of electrons. So, and we usually just use boxes to represent those. So S has 1 orbital, a P, this is not the shape of the actual orbitals, but this is just kind of how we represent them. Our P sublevel has 3 orbitals. Our D sublevel has 5, and then our F sublevel has 7. 2, 3, 4, 5, 6. I think I did too many here. There we go. Get rid of that one. Each one of those orbitals can hold 2 electrons. Now, when we're drawing what are called orbital diagrams, we show where the electrons are located in the orbitals, and we draw our electrons as arrows, and our arrows point in certain directions to represent where electrons are located. So our orbital diagrams will look something like this. And we'll talk about more in detail what that looks like for each specific element. Electron spin, you guys will notice that I drew my arrows here facing opposite direction, one pointing up and one pointing down. That's because, electrons are both negatively charged. So they do repel each other. However, if they also spin on their axis, and so when things that have electrical charges spin, then they create magnetic fields. And so if you have electrons and they both have negative charges, but one of them spins in one direction and the other one spins in the opposite direction, then they can actually have a magnetic force of attraction, not an electric force of attraction, but enough so that they can actually hang out in the same orbital without repelling each other. So when we put 2 electrons in an orbital, we want them to have opposite spins, and so we show that with our arrows pointing in opposite directions. All right, some rules when we're doing electron configurations and orbital diagrams. The lower energy levels fill up first for the most part. So that means like 1s is going to fill up first, then 2s, then 2p, then 3s, 3p. Right here is where it starts to fill up out of order. And we're going to talk about how we figure that out. We're going to use our periodic table to help us with that. But everything is going to go in order right until you get past that 3p sublevel. And then what happens is those orbitals start to overlap. And so it's easier for electrons to fill up other energy levels first. So 4s will come next, and then so on. Let's see, we've talked about the Pauli exclusion principle, that orbitals, our little rooms up here, can only hold 2 electrons. The other rule is that, number 3, Hund's rule, is that electrons will spread out if they can. Okay, so what I mean by that is, let's say I have a P sublevel, and that P sublevel holds 3 electrons. Those 3 electrons are going to go in separate orbitals before they pair up. So they're not going to do this. 1, 2, 3. That's not correct. They want to spread out if they can. They only double up if they have to. Let's go ahead and do an example with nitrogen. So nitrogen is atomic number 7. And because it's atomic number 7, that means that it has 7 electrons. So if I'm going to write out the electron configuration, I'm going to start with the first energy level and the first sublevel, which is 1s. And I know that the s sublevel can hold 2 electrons. So what I'm going to do is I'm going to go ahead and put a 2 up there and show 1s2. And the next energy level that starts to fill up is 2s. And s can hold 2 electrons. So that's 2. Now together, that's only 4 electrons, so I need to keep going. The next one that's going to fill up is 2p. P has 3 orbitals, and it can hold 2 electrons in each orbital for a total of 6 electrons. But I already have 4 that are listed in my electron configuration. So I only need 3 more electrons to give me my total of 7 electrons. So this is my electron configuration for nitrogen. And the way we would say that would be 1s2, 2s2, 2p3. If I'm going to draw the orbital diagram, I could show this box for my 1s2 or my 2 1s electrons. My 2s2 electrons, one up, one down. And this is where that previous rule that we just talked about is important. This is 2p3. I need 1 electron in each orbital before they start to pair up. The reason why that becomes important is because we're going to start to look at what are called unpaired electrons. So all of these right here are called unpaired electrons. Which means that there's an empty space in each one of these orbitals, which is going to help us figure out some bonding, how they form bonds with other elements, because there's a spot for electrons to fit in there. The other thing we need to know is a couple of other terms. All of our inside energy level electrons are called core electrons. And all of our outside energy levels, not just the outside sublevel, but our entire outside energy level, which is the second energy level. So whichever part of your electron configuration has the highest energy level number, those are all considered valence electrons. And valence electrons are outermost electrons. So nitrogen has our 2s2 and 2p3 are the valence electrons for a total of 5 valence electrons. So we're going to do a few examples, and we're going to talk about how we use our periodic table to help us with electron configuration. So let's start with sodium. When you have your periodic table, you need to find sodium on your periodic table. So sodium is right here. And so what I'm going to do, there are different blocks on the periodic table. So this blue section right here, this represents my S block. My pink section represents what is called the D block. And my yellow section represents what is called the P block. Now, you are always going to start right here when you are writing your electron configurations. And you're basically going to go across each row until you get the element that you're looking for. So the first energy level that's going to fill up is the 1s energy level, and it holds 2 electrons. After I've gone through that row, I'm going to go to the next row, and the next thing that fills up is 2s, and I can see that it holds 2 electrons. Next thing that fills up is going to be 2p, and it holds 6 electrons. And then this is sodium right here, so I'm going to end with 3s. That should be a 1. Which is correct because sodium is number 11, so it should have 11 electrons. Now, kind of a shortcut for writing electrons, which is acceptable, is to take what is called the previous noble gas, this one right here. This noble gas would be neon. I can go ahead and I can take that and put it in brackets. And then basically what you're doing when you do that is you're just saying, hey, sodium has all of the same core electrons, the ones on the inside, as neon. But then it also has an extra electron in the 3s energy level. So on the left in blue would be called my complete electron configuration. And then this would just be my noble gas electron configuration. Okay, let's go ahead and do sulfur. Sulfur is going to be right here. So I'm going to go ahead and I'm going to start with 1s and I'm going to fill it up, 1s2. Then I'm going to go to 2s, 2s2, 2p6, and then I'm going to have 3s2. And then I'm going to go ahead, the next thing that fills up is 3p, and I can go ahead and count. This is 3p1, 3p2, 3p3, 3p4. This would be my electron configuration for sulfur. If I want to write the noble gas electron configuration, that previous noble gas is neon. But then sulfur also has 3s2 and 3p4. All of these guys right here are my core electrons. All of these guys right here are my valence electrons. Okay, when you start to get to things like iron, transition metals, iron is right here. So it's a lot of work to write out the complete electron configuration. Most of the time you don't have to do that. So I'm going to go ahead and I'm just going to start with my previous noble gas that comes before iron, and that noble gas is argon. And then from argon, that previous noble gas, now I'm going to go across the next row. The next row has 4s, and that has 2 electrons. And then the next thing that fills up, this is where it starts to, in row 4, this is where things start to fill up out of order. So then my next thing that fills up is 3d. And I have 3d 1, 2, 3, 4, 5, 6, 3d 6. Now here's the tricky thing about iron, or any transition metal really. When they start to ask you about core electrons and valence electrons, even though it fills up before the 3d, my 4s2 electrons are still my valence electrons because they're in the 4th energy level. So you're looking for whichever one has the highest number energy level, and those are your valence electrons. So iron only has 2 valence electrons. Okay, let's go ahead and do one more. Let's do iodine. Iodine is right here. Let me change colors. Okay, previous noble gas for iodine is going to be krypton. So I'm going to start with that. After krypton, I'm going to go down the next row. The next row that starts to fill up is 5s. That's 5s2. Then I have all of the 4d electrons. D can hold 10 electrons. And then 5p, 1, 2, 3, 4, 5, 5p, 5. Now, looking at which ones are my valence electrons, these are valence electrons, but so are these because they're all in the 5th energy level. So iodine has 7 valence electrons. So let's go ahead and talk about ions now. Ions are similar to our electron configurations for atoms, but when we're dealing with ions, we're talking about things that have either lost electrons or gained electrons. So anything that is a positive ion is something that has lost valence electrons. Anything that has a negative charge is because it gained extra electrons. So basically, our metals and nonmetals, they're gaining or losing electrons so that their electron configurations can be like those of a noble gas. By the way, don't ever say that they turn into a noble gas, because they don't. Their number of protons still determine what the element is, but they have electron configurations that are similar because they've gained or lost electrons. So let's talk about calcium. If we were to write out the electron configuration for calcium, first of all, the calcium ion, you guys should be able to find calcium on the periodic table, and you should see that it is in the column that has a charge of +2. So that means that calcium loses 2 electrons. If I write the electron configuration for calcium, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. Now, if it's going to lose 2 electrons, it's going to lose the 2 valence electrons. So my electrons that are in the farthest out energy level are going to be lost. And so this becomes my electron configuration for the calcium ion. Okay, let's go ahead and talk about sulfur. Sulfur is in the column where it has a charge of -2. So let's go ahead and write out the original electron configuration for sulfur. So sulfur, the previous noble gas, is neon. Then I've got 3s2, I've got 3p4. Since the charge is -2, that means sulfur wants to gain 2 electrons. It's going to gain electrons right there. You should notice P is only holding 4 electrons and it can hold 6. So those 2 electrons are going to be added right there. So that electron configuration changes to 3p6. Okay, transition metals are a little bit tricky. Something like iron 3+, you always just start with the original electron configuration. So for iron, the previous noble gas is argon, then 4s2, then 3d6. Okay, but because it has a charge of +3, it means that it needs to lose 3 electrons. Now, going back to our previous slide, I think, talking about transition metals, they always lose their valence electrons first. My valence electrons are the ones in the highest energy level. That means even though it filled up first, the electrons also get lost first from the 4s energy level. So those 2 go away, but that's only 2. Iron needs to lose 3 electrons. So it's going to lose 1. Once their valence electrons are gone, then it can start to lose core electrons from the D sublevel. So now I can go ahead and lose 1 more electron from the 3D sublevel. This will become 5. So my new electron configuration is going to be argon 3d5 for my iron ion. And this is actually really important. There's always a transition metal ion question on the AP exam. And it's because they know people miss it a lot because they take away electrons from the last one that was filled instead of their valence electrons. So just be really careful with that. Go ahead and take some time, pause the video, and work through these practice problems right here. Go ahead and write the electron configurations for each one of those ions. Oh, and you know what else I should say? This is important. Like for calcium, if you notice these core electrons, this is the same as the electron configuration for argon right here. But when you're writing electron configurations for ions or any atom at all, you can't just put the noble gas in brackets and leave it there. You have to show more of what's going on with the electrons. So you can't do that. So keep that in mind when you're writing these electron configurations right here. So this is the last section of the notes that we're going to go through. I know that it's been a little bit long, but that way when we come to class and do the next section, we'll know what we're talking about. We'll review ionization energy. So this definition, just make sure you understand what it is. Ionization energy is how much energy is required to remove an electron. So, you know, atoms like to hang on to their electrons, and some atoms hold on really tight and other atoms don't hold on very tightly to their electrons. Atoms that hold on tightly to their electrons have very high ionization energies. And then those would be like our nonmetals are holding on tightly to electrons. Metals have low ionization energies. They let go of their electrons very easily. But there are these things right here, I1, I2. You need to understand that. So first ionization energy, how much energy does it take? And we're talking about energy in terms of like kilojoules or even megajoules. How much energy does it take to remove the highest energy electron? So if I take 1 electron away, how much energy does that take? Now, once that first electron is already taken away, now if I go in and I go to take a second electron, the amount of energy it takes to pull the second electron away is called the second ionization energy. So something that's really important to know is that the second ionization energy is always greater than the first ionization energy. When you take away 1 electron, that second electron is either in a lower energy level or the atom has gotten smaller in size because that first electron is gone. It's always closer to the nucleus. The closer an electron is to the nucleus, the harder it is to remove. So if there's a third ionization energy, if you go to take a third electron away, that's going to take more energy than it took to remove the second electron, and so on. The more electrons you remove from an atom, the harder it gets. Okay, so when we get to class, we're going to do some practice with the electron configuration, and then we are going to go through the section of notes on 1.6 together in class, and we'll be doing lots of practice with this. So I will see you guys in class. Have a good day.